In this video, we're going to take a look and see how to find the derivative of a polynomial. So just a reminder, the definition of a derivative for a polynomial or any type of function is the derivative f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So we've used this definition previously. Now what we want to do today is figure out, is there an easier way with specific types of functions, such as polynomial, to find the derivative without having to use this long definition? So I want to take a look at some notation for derivative. So if your function is f of x, f prime of x is a notation for derivative. If your function is y is equal to something, y prime, another notation is dy dx, the derivative of the function y with respect to x. So we may see the dy dx notation a little bit more in this chapter. It means the same thing as y prime. If you have something like an equation y is equal to x squared, you might see the derivative as dx squared over dx. They may put the function in, the derivative of the function x squared with respect to x. It may be written dy dx, and it may be written y prime. So just to be able to distinguish between the different types of notation, they all mean to do the same thing. So the meaning of a derivative is the slope of a tangent line at any particular point on the original graph. What that also means is an instantaneous rate of change of y, the dependent variable, with respect to x, the independent variable. Average rate takes place over an interval, and instantaneous rate takes place at an instant or a single point in time. So the types of functions we're going to look at today are polynomials. So polynomials are of the form f of x equals a x to the n plus a sub 1 x to the n minus 1, etc., wherein the variable up top, x to the power of n, the n is an integer, a positive integer. So examples of things that are polynomials, okay, things that you have worked with. A linear function is a polynomial. Y equals 4, that's a linear function. Y equals 2x plus 1 is a linear function. Quadratics are polynomials. Something like 3x squared plus 2x minus 1 is a polynomial. And then we can keep adding any degree. Y equals x cubed is a polynomial. We just make sure that your values for n minus 1, n minus 2, are 0 or greater. So things that are not polynomials, things like y is equal to 1 over x is not a polynomial, because that would be x to the negative 1. Anything that has x to negative powers, fractional powers, decimal powers are not polynomials. All right, so let's take a look and see what the derivatives look like with the functions that we're familiar with. So if we take a derivative of a constant function, let's take a look at that. Y is equal to 4 is a constant function. The graph of that is a horizontal line through 4. The derivative represents the slope of a tangent line. So wherever you choose a point on the line, you still get the line itself. So the derivative is the slope of the line, which is 0. So the slope of that line is 0. So the derivative, y prime, is equal to 0. And then that leads us to the derivative of any constant is equal to 0. So the derivative of a value like 4, 2, 1, pi, the derivative of that is 0. If we have a linear function in the form mx plus b, let's take a look at f of x equals 3x plus 1. If we graph that, 3x plus 1 has a slope of 3. The slope of a tangent line anywhere on this graph, again, a tangent line is the graph. So the derivative of this function is going to be the slope. So the derivative is equal to 3. The derivative of a quadratic function and higher degree polynomials, quadratic is something a little bit different. So when we graph x squared, it depends on which point you pick. So the slope of a tangent line at the coordinate 2, 4 is going to be different than the slope of the tangent line at the point 1, 1 is going to be different than the slope of the tangent line at the vertex. So the slopes of the tangent lines on f of x equals x squared are different depending on where you're at. So we're going to end up having a function. So we're going to talk about how you find the derivative of a higher degree polynomial, and then we'll go back and find the derivative of the example. One thing we always could do is use the definition for a derivative. The limit as h approaches 0 of f of x minus x plus h minus f of x over h. Okay, so if we did that here, what we would end up with, if you go through, we would have x plus h squared minus x squared over h, just substituting the values in. X plus h squared would be the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. The x squareds would cancel each other out. The limit as h approaches 0 of this function, we could divide each of in the numerator by h, and we're left with 2x plus h. And the limit as h approaches 0 is 2x. So f prime, the derivative is 2x. So if I pick a value such as 1 when x equals 1, the slope of the tangent line at 1 is f prime of 1, which is 2. The slope of the tangent line at x equals 2 is f prime of 2, which would be 4. So this equation tells us the slope of a tangent line anywhere on the equation x squared. But what I'd like to do is have a shortcut instead of having to use that definition of a derivative every time. And what the shortcut is, here's the property. The derivative of a power of x, the derivative of x to some power of n, is equal to n times x to the n minus 1. Another way to think about that is, if y equals x to the power of n, then y prime is multiply the power in the front times x and subtract 1 from the power. So let's try that on our x squared function. If y is equal to x squared, then the derivative is take the power of x, multiply it in the front, 2 times x, and then subtract 1 from the power. That was a lot faster than using the definition. So the wonderful thing about finding derivatives of polynomials is we can use this derivative of the power of x property along with a couple of other properties and find derivatives of polynomials very quickly. So next example, find the derivative of the function v equals r to the 10th. So I'm going to use notation dv dr, just to change up notation, equals multiply 10 in the front times r, and then subtract 1 from the power. 10r to the 9th is the derivative. So when we're taking a look at polynomials in the goal, let me take a look down here. The goal is example 5. We'll have a polynomial written that has multiple terms. You're multiplying numbers in the front. You have various powers. So how do we handle each of those? So there's a couple of properties. The first one is the derivative of a constant times the power of x means that you take the derivative of the x term and it's still multiplied by the constant in front. What does that mean? If we take the derivative of y equals 3x squared, y prime is equal to 3 times the derivative of x squared, which is 2x. So our derivative is equal to 3 times 2x, which is 6x. So if you have a constant times your variable to a power, you take your constant times the derivative. If you're adding or subtracting terms, this notation says take the derivative of each term separately and add and subtract them. So example 5, now we can find the derivative of a polynomial. It says evaluate the derivative at the point -2, 15. So what we want to do is we want to find the derivative. So we're going to find f prime. And then after we do that, we want to know f prime of -2. What is the slope of the tangent line at the coordinate -2, 15? So to find the derivative, we have 2 times x to the fourth, so that's going to be 2 times the derivative of x to the fourth. Multiply the 4 times x, drop the power by 1, minus 6 times the derivative of x squared, which is 2x, minus 8 times the derivative of x, that's x to the power of 1. So when we multiply the 1 in the front, we get 1 times x to the 0. Anything to the power of 0 is 1. And then the derivative of -9, -9 is a constant, so the derivative of -9, or 9, is 0. So to clean up our answer, we end up with the derivative as 8x to the third minus 2 times 6, which is 12x, minus 8 is basically the x to the 0 is 1, and that's our derivative. So that tells us the slope of a tangent line anywhere on the curve given above. So to evaluate the derivative at the coordinate -2, 15, we substitute -2 into our derivative. So we get 8 times -2 cubed minus 12 times -2 minus 8. -2 cubed is -8. 8 times 8, that's -64 plus 24 minus 8. -64 plus 24 is -40 plus 8 is -48. So the slope of the tangent line at the coordinate -2, 15 is -48. All right, last example is an application problem. It says for each 4.0 s cycle, the displacement s in centimeters of a piston is given by the formula s equals t to the third minus 6t squared plus 8t, where t is the time. So think about the piston moving up and down. Find the instantaneous velocity of the piston for time equals 2.6 seconds. So to figure out how fast the piston is moving at any point in time, we take the derivative. So we're going to take s prime, or ds dt. Just depends on which notation you prefer. So the derivative of t to the third is 3t squared. The derivative minus 6 times t squared, I'm just going to multiply 2 times -6 is -12t. The derivative of 8t is plus 8. So that will tell us the speed of the piston at any time. If we have time equal 2.6 seconds, then substitute 2.6 for t, and that will tell us the speed of our piston at any time. So I'm going to go ahead and throw that in the calculator, get an answer, and then I want to make sure that we can label our answer. So I'm going to put 3 times 2.6 squared minus 12 times 2.6 plus 8, and I end up with -2.92. So that tells us that the piston is traveling downward because it's negative, and now we need to label our answer. So remember that slopes are horizontal or vertical over horizontal. So we want to have our centimeters. That's what we're moving in. So it's moving in centimeters per second. So make sure you also label your units on a word problem or an application.